Thanks a lot. So let me start by thanking the organizers very much for giving me the opportunity to be here and the chance to even speak here. Although it's challenging with this hybrid mode and everything, but it's great that it works out. So thanks a lot. And what I'm going to talk about today is mainly, so the main part of the talk will be taken up by modeling. So, and it's modeling in a twofold way, namely, pointer. No, sorry. Here's a pointer, but I don't know how to, which buttons, I'm sorry, do I have to press to point?
I think here.
Okay. There's something like.
No. I think here you for the point.
Maybe I just try using the mouse. Yes, I think this works. So thank you very much. Sorry for the delay. So it's twofold, namely it's about nonlinearity and it's about fractional damping. And both play a role in imaging modalities because in ultrasound, as soon as the intensities get higher, which is somehow needed in novel technologies to get enhanced images, one has to use nonlinear models. And also the damping is something which does not in reality follow this classical integer strong or weak damping law, but usually it's in between, and then it's fractional damping. So I will look at actually two imaging modalities, so to say. One is photoacoustic tomography, which is meanwhile well known. But what we did in addition is to include this fractional damping aspect and also a novel technology that is called nonlinearity parameter imaging, and you will see in a moment what it's all about with this nonlinearity parameter. First of all, about nonlinear sound propagation. So this is an image of a simulation, or these are three snapshots of a simulation of an acoustic wave that has been excited in a sinusoidal way here on the left, and it's propagating to the right as time proceeds. And as you see, well, it's propagating as expected with a bit of damping. The amplitudes get less, but in particular also the profile changes. So it's first of all here on this side where it continues to be excited, it's sinusoidal, but over here it becomes, well, this triangle shape. It's actually called a sawtooth shape because it looks like a sawtooth for obvious reasons. And so why does this happen? In principle, the principle is that the wave speed depends on the amplitude, and it depends actually on the signed amplitude or on the signed density. So in regions where the medium is more dense, it's densified by the wave propagation, there's faster propagation, and in regions where it's rarefied, it's slower. And so you see the wave propagation in the here is a bit faster than up here, and so they start to overtake each other, so to say. So of course overtaking does not take place, but the change of profile that is really visible. And actually one can see this also in the equations later on. No, the wrong, so this way. In the sense that the wave speed depends on the state. So to derive acoustic equations, one has to go back to the fundamental balance laws of acoustics and to the fundamental quantities that are of importance here. And that's first of all the acoustic particle velocity, then the acoustic pressure and the mass density. And they are all functions of space and time. They evolve around a mean part that is constant in space and time, especially for the pressure and for the mass density. So there's fluctuation around constant parts. For the velocity, this is not the case. It would be the case if we would have some flow, but we don't consider this here. So the velocity itself, so to say, is a fluctuating quantity, fluctuating around zero, so to say. And then, too many buttons to be pressed. Okay, sorry. And then, so we have the quantities now. We have to equip them with equations. And these are balance equations, balance of momentum and balance of mass. That's the two key equations. As long as one considers these three quantities, one can also consider more, temperature and so on and so forth. Then one also has to look at energy balance. But for now, let's only have a look at balance of momentum and balance of mass. And then there's, of course, constitutive modeling, so to say. So we have to find a relation between mass, density, and pressure. And it's actually, so to say, relative mass density and relative pressure. And there's, in general, a nonlinear relation. So for deriving linear acoustic equations, one uses a linear relation, just this first part here. But then one continues, and it's actually coming from some sort of Taylor expansion. That's why physicists just use these letters capital A and capital D for the first, second, and so on. There's also a C part if one wants to consider it Taylor terms. And then after certain elimination, we end up with this form here. And so this B over 2A or B over A is that nonlinearity parameter. So putting this together is basically by combining these two equations and then plugging in this relation down here. So combining these two equations, what we want to get rid of is actually the velocity. And it's easy as long as this nonlinear term here and this viscosity term over here can be neglected. It's easy because we just have to take the divergence of this equation and subtract it from the time derivative of this equation. And then the velocity is gone. And then we have an equation in terms of p and rho, and one of the two can be removed by this last identity here. So if one does so, one ends up with the classical wave equations of nonlinear acoustics. The first of these is Kuznetsov's equation. And so that's an equation for the pressure and also still for the velocity, because recall we cannot completely remove the velocity over here. So there's a bit of velocity left even after elimination, so to say. No? Okay. Now I've lost control. So I'm not a control person, just an inverse problems person. And so, that's safer. Yes, thank you very much. I'm sorry for my clumsiness. Okay. Here we go. Okay, so in this Kuznetsov equation, on one hand, you see there's the velocity also left over, so to say, even after the elimination process. You also have this nonlinearity term. Well, actually, this term is by nature, so to say, nonlinear, and this one too, by modeling. Both are square nonlinearities. And then, this one also contains the nonlinearity parameter. And then you have the pressure, and if you just look at the pressure over here, and if you neglect these nonlinear terms and also this strong damping term, then you see it's just the simple linear wave equation. So that's the relation between the linear and the more general nonlinear model. One can also go back to just one scalar unknown by using the acoustic, using the fact that the particle velocity is irrotational, so it has a potential, a scalar potential. So, and the scalar potential is called velocity potential. And plugging this in up here and doing one-time integration, we end up with this, so to say, classical form of Kuznetsov's equation just in terms of the velocity potential. Another way of getting rid of the velocity term over here is by doing a further simplification, which is physically justified if one neglects local nonlinear effects. So one replaces basically this squared velocity term, so the one up here, by something in terms of the pressure, and then one ends up just with this quadratic pressure nonlinearity, and that's the Westervelt equation. So these are really the two classical objects that one studies in nonlinear acoustics. But there's further possibilities. So as I mentioned, one can do further modeling by taking temperature into account, for example. And that's then, one ends up with higher order models, such as the Blackstock-Crichton, or also called BCBJ for abbreviation, equation. You see, you literally see there's temperature evolution involved because there's a thermal conductivity and there's this heat operator here in front. That's why I've written it like this. And another way is to introduce a relaxation time, because in the classical models, due to the strong damping term here, this one back here, where is it? Up here, this one. There's infinite speed of propagation, so the equations basically behave like parabolic equations, which is not natural. So, of course, acoustics sound propagates at finite speed, and in order to take this into account, one introduces a relaxation time, and then one ends up with a third order in time equation. So these are just to compare with Kuznetsov's equation. By formally setting the relaxation time to 0, one comes back to this classical model, and also by putting the thermal conductivity to 0 and doing one time integration, also it's Kuznetsov's equation. And one can do this not only formally, but also mathematically rigorously in appropriate function spaces. So the tools are here to derive uniform energy estimates and then take weak limits. Okay, this is just still incomplete list. It's just to demonstrate there's a lot of things going on here, and especially it's a nice playground to do mathematics on these equations. But let's, instead of looking at this huge list, let's just look at the equations, because this is what we like to do, I think, and why they are sometimes not so easy to analyze. So the point is we have this nonlinearity. It's a quadratic nonlinearity, and it appears under the second time derivative. So I have written this more clearly here, so using a combined coefficient that actually contains this nonlinearity parameter. And so you see we have a u squared tt on the right-hand side. And so if we move everything to the same side, then you see already there is potential degeneracy involved here. So there's u minus something times u squared under the second time derivative. And doing some further elimination steps, one even sees, so we now we differentiate this out and then we divide. And from here you see that the sound speed, the effective sound speed, really depends on the state, which is the acoustic pressure here, so the fluctuating acoustic pressure, this way. So that's the, so to say, the formula for the effective sound speed in this damped wave type equation. Also the damping depends on this, but mainly it's the sound speed that is important here. And you see as u is as long as u is small enough, everything is fine, because 1 minus 2 kappa u is then still positive. But as soon as the u becomes too large, taking the square root doesn't work out anymore. Mathematically speaking, physically speaking, the model is just simply not valid anymore. So one has to take care of this also mathematically. And one of the key tasks during any well-Postness proof is to really get an L-infinity bounds on u in order to make sure that nothing goes wrong with this division by something maybe close to 0. Okay, so this was about nonlinear modeling. Now let's proceed to fractional modeling. So it's about actually fractional damping models. And I will start off with where, so to say, historically, fractional damping models occurred first, namely in elasticity. So that's where Caputo rediscovered fractional derivatives, and you have seen very nicely in yesterday's talk how these fractional derivatives are defined. I will come to that. But let's first of all stay with classical derivatives and look a bit into elasticity. So there you have the equation of motion. So U plays the roles of the mechanical displacements. It's a vector of displacements. Sigma is the strain tensor. And so you have this equation of motion here driven by some force, some volume force possibly. And on the other hand, you have the strain tensor, which is, so it's actually the geometrically linearized version already of the strain tensor with the symmetric gradient of the displacements. So these are inherently integer derivatives, nothing to be fractionalized here. So let me insist on this point, because as you might recall, whenever we have a divergence in the equation, it comes from using volumetric balances, so looking at an arbitrary test volume and taking a balance over the test volume flux through the boundary, and through Gauss divergence theorem, from this flux through the boundary we get a divergence term. Somehow, to some extent, similarly also in elasticity, and then it's really the classical divergence and nothing else. And likewise, this gradient of the displacement is the strain. That's, so to say, just a mean value theorem, or more or less, that we are using, mean value theorem of differentiation. However, there's also a third equation, like before, that we need in order to link things together, and especially to link stress and strain. That's the classical constitutive modeling in continuum mechanics. And there one indeed has some freedom to also use fractional derivatives. First of all, let me start off with integer models. And here's a list. So the first of these is the classical Hooke's law, which just gives a linear interrelation between stress and strain. I've written down everything in terms in 1D, not in order not to be bothered with tensors and so on and so forth. So we just have this linear relation between stress and strain. It's classical elasticity. However, one could also think of relating not the strain itself, but the strain rate to the stress. That's then Newton's model, or a combination of strain and strain rate, Kelvin-Voigt, or the other way around. So stress and stress rate combined gives the strain. That's the Maxwell model, or on both sides a combination of both. And actually here, these integer derivatives, you see, by doing this combination, one tries to reach some sort of interpolation. It's very legitimate to also use fractional derivatives. And people have been doing that. So there's this fractional time derivative appearing here. And actually, one could clearly go ahead and say, well, instead of just having a combination of a zeroth and some non-zero fractional derivative, one could have a linear combination. And at the very end, you will see one could even have convolution with arbitrary memory kernels here. Okay, how to do this in acoustics? So just recall, we return to linear acoustics for simplicity. So we have the linear balance of momentum, the linear balance of mass. And then for linear acoustics, it would be just a linear equation of state, so the linear constitutive model linking the mass density and the pressure. And so we can replace this by some more general fractional model. So inserting these constitutive models into, again, the usual procedure, taking the divergence of this and subtracting the time derivative of this in order to remove the velocity, we end up with fractional models of acoustics. Here's a list, and so maybe the only thing to keep a bit in mind is the one below, so one can go very general and use a combination of fractional derivatives both on the higher than 2 order time derivative side and also on the adding, so to say, a time derivative to the space derivative part. So what are these time derivatives? We have seen them already yesterday. They are all based, it was also nicely mentioned that historically they go back quite far. And so here the first anchor point is already after, well, at least a century with Abel, who invented the Abel integral operator, this one here. And based on this, the Riemann-Liouville and the Jabashan-Caputo derivative. So I'm also mentioning the name of the Armenian mathematician Jabashan because actually he has done a lot of very useful work which was somehow unknown in the West for a long time for the usual reasons. Okay, the question is, you see how they are linked, so to say, in order to get a fractional derivative of order alpha, you take a time derivative, you sort of compensate for it with one integral, and then you do a negative integral of order alpha, so to say. And the question is whether you do time differentiation before or you do time differentiation after applying the integral operator. So the advantage of doing it afterwards is, of course, that after doing the time integration, it's more likely to be, the function is more likely to be differentiable. However, the disadvantage is, as one can easily compute, if you take, for example, the constant 1 function here, take the integral and then differentiate, what you get is a singular function. You get a function with a singularity at 0. T to the minus alpha singularity, which is not natural. So usually one would expect that the derivative, any kind of derivative of a constant function, should be 0. And that's actually what happens, as one also easily sees by using the Jabashan-Caputo derivative. So when looking at inverse problems, these fractional derivatives play an important role, and who knows it better than my chair, that this is the case. The important thing is here, due to this integral here, which goes over the whole time horizon, so this one here, it goes from a to t, this derivative altogether is a non-local one. So it takes into account values that are back in time, even up until the initial value. And for example, if one wants to reconstruct something which lies in the past, of course this helps because the derivative carries along information on the past. And so final time values allow, so to say, more easily, and also really in a strict mathematical sense of stability, to more easily reconstruct initial conditions from final time data. An example for doing that is photoacoustic tomography. So photoacoustic tomography is about reconstructing an initial pressure from measurements along the timeline at the boundary, as we will say mathematically. Physically, it's some array of piezoelectric, usually transducers, in order to record the pressure. So it's if you are in d space dimensions, it's a d minus 1 dimensional set. And in order to recover some initial condition, this is a function of d variables, we make up for the missing dimension by using the timeline. And this works out, so there's uniqueness proofs and so on and so forth about this. And as long as there's no damping, this is even an almost well-posed problem. So one just loses 2 derivatives. But as soon as damping is around, and this is naturally the case in ultrasonics, the problem becomes severely ill-posed. And especially if it's strong damping, then you have exponential ill-posedness, so meaning exponential decay of singular values that you have to invert during the reconstruction. So what we looked at is to what extent this damping, so you doing a realistic fractional damping as it's mandated in ultrasonics, how the order of differentiation influences the ill-posedness of the inverse problem. The expectation is that if you have a stronger memory, then ill-posedness should get less. So if we have an integral kernel with less singularity, then we should also get a more well-posed inverse problem. Wrong direction. Okay, that's the questions that we posed ourselves. And so let's have a look on how far I can proceed into this. Okay. So that's the problem setting. So what you have here is the wave equation now written with an abstract operator A, which is the negative Laplacian with homogeneous, for simplicity, homogeneous Dirichlet conditions, but actually impedance conditions would be more appropriate and also work out here. So we have the Laplace operator here, so then it's a positive definite operator A. And we have a damping operator acting, and what we want to reconstruct is the initial data, U0. What we have available is measurements on this boundary part, or actually it's not really a boundary of the domain, it's some d-1 dimensional surface immersed into the domain on the timeline from 0 to t, or ideally from 0 to infinity. Okay, to also add fractional damping, we use some of the models from before. So the classical one, more or less classical ones, are these Caputo-Wismar-Kelvin damping, where you have a fractional order combined with the Laplace operator. The Zener model that we have seen before leads to this damping model, so a combined 2 plus alpha order with respect to time, or beta order with respect to time combined with the Laplacian. And there's also the possibility to apply a fractional Laplacian, the fractional Laplacian that I'm referring to here. So there's many options on finite, on bounded domains, but the one that I'm referring to here is simply the spectral one, which means that this operator has the same eigenfunctions as the original operator A, but the eigenvalues are taken to the power of beta tilde here. So sorry, I ran out of letters. For some reason, I didn't want to use gamma here. So it's a beta tilde. Okay, these two can be combined actually. No. These two can be combined clearly, and then it's a model with a long name, which I just abbreviate by CH. Okay. So these two things, this is what we studied more closely. And actually, it does play a role what form this damping has, because later on we are going to look at Laplace transformed versions of this. And then these fractional derivatives become powers, fractional powers of the Laplace domain variable, so to say the frequency. So the important ingredient for uniqueness proof is this one here. So that's what we called the linear independence condition. Maybe you have a better name for this, but it's really about linear independence. It's linear independence of eigenfunctions, namely for a fixed eigenvalue in higher space dimensions, the Laplace operator will typically have several eigenfunctions. The dimension of the eigenspace will be larger than 1. It will be 1 in one space dimension, but in higher dimensions it will be larger than 1. Still finite, but it will, so the set of eigenfunctions corresponding to a fixed eigenvalue lambda consists of possibly several eigenfunctions. And of course, the eigenfunctions are orthogonal to each other, so they are clearly linearly independent. But the question is, what happens if we restrict them to the observation surface? So they might actually, if one is sort of clumsy, and I'm good at being clumsy, as you can see, it could happen that they suddenly become linearly dependent by just doing, choosing sigma as a zero set of eigenfunctions. So this should be avoided. So clearly there must be a geometric condition in order to get uniqueness, and this is, so to say, our geometric condition here. And what one gets out of this is really uniqueness. So assuming that the domain and the operator are known, I will mention about also some unknown pieces, potentially unknown pieces in the operator as well later on. But let's assume for the moment this is known. Then the linear independence assumption yields uniqueness of reconstruction of this initial value, the initial pressure, from the time trace measurements on this surface. And let me just give some remarks and maybe also a quick idea of the proof. So this linear independence assumption is clearly satisfied in 1D, because in 1D per eigenvalue we just have one eigenfunction. And this is non-zero and therefore linearly independent by definition. It's also possible to prove this linear independence condition in certain geometric configurations. So if one looks at, for instance, circles or spheres, then one can compute the eigenfunctions of the Laplacian. One can express them in terms of Bessel functions, for example, and then one can give, so to say, a recipe on how to choose the sigma surface in order to avoid linear dependence. On the other hand, it's a condition on zeros of eigenfunctions, because as you see here, you have we are dealing with linear combinations of eigenfunctions, and clearly linear combinations of eigenfunctions are eigenfunctions again of the same eigenvalue. And so it's also related to the question of zeros of eigenfunctions, which has also been studied in the literature. Now about a different topic. So I said before in the theorem we assume for simplicity the operator is known. Well, if it's the Laplace operator, it is known, but it could be that it's a operator with a time-dependent coefficient, space-dependent coefficient. For example, the sound speed. So if you have an inhomogeneous medium, then of course the sound speed will depend on space. And if you don't know the medium in advance, you don't know the sound speed, the spatial dependence of the sound speed. And so an interesting additional problem is actually to reconstruct the sound speed itself. And it's actually possible based on the knowledge that we have using inverse Sturm-Liouville theory. So because from these same observations, what we get is not only the information that we need for really reconstructing the initial condition, but we also obtain the eigenvalues of this operator and also endpoint data of the eigenfunctions. And according to inverse Sturm-Liouville theory, this provides us with space-dependent coefficients inside that operator. So finally, let me just mention about what tools we are using in the proof. So we use a solution representation by separation of variables. So we write the solution of the PDE as a series expansion in terms of the eigenfunctions. And then what we also do is to Laplace transform the thing, to look at the whole thing in Laplace domain. And then it's about location of the poles. So the important information sits in the poles, so in the singularities that appear in the Laplace transformed functions. And then an important finding is that we can uniquely recover the eigenvalues from these poles, and we can also directly recover the coefficients, the Fourier coefficients of that initial condition U0. Okay, I don't think that I have any time to go through the proof. No, time is almost up. So sorry for that. Maybe just to give you a glimpse on what I mean. So that's this separation of variables that we are using here. And actually, as soon as we have gone there, we are with a system of ODEs. So this allows to reduce the whole problem to a system of ODEs, with these lambdas, so to say, replacing the operator A. And then this can be solved in Laplace domain, leading to the Laplace transformed relaxation functions. And the poles of these relaxation functions are the important information, so they allow us to distinguish between different eigenvalues. And also the residues at these poles, they don't vanish, that's important. Okay, no more details about this proof. Let me just come back to that question that I posed at the beginning of this section, namely on how ill-postedness of the inverse problem depends on the strength of the damping. And the strength of the damping is governed by these powers, beta and beta tilde. So this is now the lengthy CH damping model. So we have a time derivative of order beta, accompanied with a space derivative of order basically 2 beta tilde. And the larger these betas are, they are strictly between 0 and 1, or they're actually between 0 and 1, also allowing for 1 as a value. The larger these are, the stronger the damping is. I'm sorry. And you see this also in the location of the poles. Why is the location of the poles important here? So if you have a pure wave equation, then the poles of these relaxation functions are on the imaginary axis, because the Laplace transformed equation is just, this is just s squared minus lambda times the Laplace transformed solution is equal to 0 or something. And then the poles, the zeros of s squared minus lambda, these are on the imaginary axis. And that's actually the well-posed case, because inverting the Laplace transform, of course, you know that's a severely ill-posed problem, but not if we have values on the imaginary axis. Because there, the Laplace transform is identical to the Fourier transform, which is very nicely and very stably invertible. And that's what is also visible here. So if you have weak damping, so if beta and beta tilde are close to 0, then we are close to the imaginary axis, and the problem is nice, so to say. But the stronger the damping is, the further we move away from the imaginary axis. So this is for varying beta and beta tilde. Now it's also important what the sound speed is. So it's also clear that the larger sound speed counteracts damping. So if you have more emphasis on sound propagation, the damping doesn't take effect, so to say, so quickly enough. And that's what one also sees, while the shape of these curves here and here is similar, but the scale is very different. So one can go up to 160 in the imaginary, on the imaginary axis, as compared to only 30. And this also corresponds to the number of Fourier modes that one can actually recover from noisy data, for example. So let me switch over this. Let me just give one slide on what it's about, this nonlinearity parameter imaging. Now we are back to the nonlinear acoustic equation. We have this kappa here, this coefficient that is space dependent. So the nonlinearity in the material depends also, it's a material dependent property, which is nice because one can use it for imaging. And people are actually using this already for doing imaging. So mathematically, the problem is about recovering this coefficient kappa of x in this nonlinear damped wave equation here. The observations are the same as before in photoacoustics. So again, we have this transducer array, and we can measure over time. And again, it's ultrasound, so we have to introduce this fractional damping, for example, these models that you have seen before. So just the key things here is the model equation itself is nonlinear, and the coefficients that we want to recover appears really inside the nonlinearity. And also we have as I told you before, so for making up the, so to say, if you're in 3 space dimensions, if you're in Euclidean space, we have a 2-dimensional transducer array. So to make up for the 3rd dimension, we measure over time. However, this works out in principle as far as uniqueness is concerned, but the ill-postedness becomes severe. And again, the question is, how does the degree of damping influence this ill-postedness? Let me mention joint work with Masahiro on this, actually even on a higher order model, and reconstructing the nonlinearity coefficient in a linearized version of this. And let me also mention recent work with Bill Randell, where we looked at both the integer and the fractional damped version of this. We also made some reconstructions, but let me skip over this because I would really like to come to this last slide, giving you a flavor of the fact that there's many interesting problems around here, and we have been looking at, for example, a small portion of them, I suppose. And one of the questions that arise very naturally, also in the context of modeling, is what are these fractional exponents here? So what are the differentiation orders? So of course one can assume to know them, but well, how to really extract them from measurements is not always so clear. So why not do it mathematically? And this is again based on seminal work by Masahiro and co-authors, where they did reconstruction of the fractional order of differentiation for subdiffusion equations. There has been much work done in between. So the one that inspired us recently was the one by Bang-Chi Yin and Havarkian, also very recently, to look as a multi-term fractional problem here. This was done for subdiffusion, and we did this for wave equations, which makes things different in many senses, and found out that by appropriate measurements one can also recover these coefficients. Also about modeling, you have seen that basically the nonlinearity in the equation came from so to say physical modeling by Taylor expansions, because that's what physicists like a lot. They learned this in the first term of their study. And but actually, why not just there's a delay here. So the more general thing would be to make an ansatz with a general function f that links pressure and mass density. And we looked at this and actually at the reconstruction of this function f, again from boundary data, and that's also a result that we had recently. And finally, let me come back to this idea of using kernels, memory kernels, instead of these linear combinations of fractional derivatives. So clearly, for example, looking back here, an even more general approach would be, so what we're doing here is we do a convolution of that Abel integral kernel with a time derivative. So why not, instead of taking this linear combination, just take a general kernel function here and do a convolution with the time derivative. And we actually did this in the context, again, back to viscoelasticity, where we have actually 2 choices of kernels, and looked at the reconstruction. Actually, it was numerical reconstruction and a bit of uniqueness proofs for reconstructing these kernels here. Looking at the forward problem, we came across, well-known publications by Pierre Marco, and this gives me the opportunity of, as many of us, we know Pierre Marco for many years already. I do so too. But the nice thing is that actually quite recently I got the nice occasion to look in a certain aspect of his really broad work in more detail, and these were the things that really helped us in the forward proof here. And so this gives me the occasion to also say happy birthday, and also say thank you for the beautiful mathematics that you have given to us so far. And of course, we are hoping for more. So, and let me thank you, all of you, for your attention.
Thank you very much. Now I remember some difficulty of the remote chair because I cannot look at the audience hall so much. Therefore, maybe I would like to ask Giuseppe to assist the discussion session. Yeah. Now, do you have any questions or comments? Giuseppe, please assist me. Because it's very difficult to recognize who wants to ask the questions.
Please, we can try.
Yeah.
The audience. Okay, I put the audience.
Now is it okay?
Hmm?
The audience. Can you see the audience? Okay.
From the audience? Oh, now I can see. Do you have any questions or
Okay.
any comments?
Anyway,
If not, oh, please.
I went over time, sorry.
But
Masahiro, you have to apply stronger control from remote. So, of course, I see it's different to control the speaker.
If no question from the audience, I would like to ask you, one question or two questions. And first of all, thank you very, very much for your very excellent talk, comprehensive survey, and also updated status of the researches, covering, say, Pierre Margot circle. And thank you so much. Then I would like to ask you one question. As for the inverse problem, the determination of the initial value.
Yes.
And some linear independence on the boundary of the eigenmodes. Then my question is that if we assume that all the eigenvalues are simple, then that condition is automatically satisfied.
Exactly. Yes. Exactly.
Yeah. Then you may feel that such a assumption might be too strong. Yeah, of course, restrictive. But I would like to give a comment. I know some classical result in differential geometry, 70s. If you are interested, I can send a PDF file, namely by Alba. Roughly speaking, generically speaking, all the elliptic symmetric operator, all the eigenvalues are simple for generic class of elliptic operator. Therefore, I think not always, but all the eigenvalues are simple is not so peculiar assumption.
Yes,
Yeah.
yes. Well, actually, we are in the course of sort of looking into this also differential geometry and so on things, and there's also some, so to say, reassuring results also on the fact that if you take, so to say, a generic surface, then it will not be a zero surface of the eigenfunction. So this is also something which gives some hope that this condition might be, so to say, generically satisfied. But of course, one can always have bad luck and pick the wrong surface and then.
And of course, one naive example is that the rectangular case in two-dimensional. Maybe the ratio of the two sides are rational.
Yes, exactly. Yes, it's about also the rational relations between the two sides and picking them.
Then quickly, I'd like to ask the related but the second question. If we replace the observation, not by the boundary, but some small interior domain, subdomain, that condition, under the same condition corresponding, you can prove the uniqueness.
You mean you assume that you have observations on a subdomain with non-empty interior?
Yeah.
Yes. This works too, because then you have the advantage of, it's again one can resort to that linear independence condition. That's then for sure satisfied.
Yeah. Also,
Yes,
one
yes.
can use the unit continuation for the. Okay, maybe later.
Yes.
Let us discuss it. Yeah. Thank you very much. And yes, if you have no other questions or comments, it's okay. Then we'd like to thank Professor Kaltenbacher once again, and thank you so much.